Okay. Can you can you just confirm which screen you can? You can see what I think you can see. Great. Can you hear me?
Yep, we can hear.
Excellent, great. So thank you, Chiao. I'm Tom Callender. I'm a clinical academic. I split my life between the UK Department of Health, where I'm involved in screening policy in the UK National Screening Committee Secretariat. And the other bit of my career at the moment is at UCL and, as Chiao said, as a long-time collaborator at Cambridge. Today, I'm going to talk to you about automated machine learning and its uses in risk prediction in healthcare specifically. And I'm going to focus on risk prediction in quite a broad sense. So I'm not going to be looking at the uses of it in, say, treatment effects and various other bits like that. I'm much more interested in the broad population scale aspects and how we can use this. So the first thing, and if all you remember from this talk is this slide, it will make me very happy. So personalization is the future of medicine. And what we mean by that is true personalization from cradle to grave of everything from screening and early detection. So you should in future have a situation where your risk is assessed dynamically over time. This then determines what you should be screened with what intervals, at what ages. And then if you develop diseases, you can use risk prediction and personalization to work out which treatments you should have, and then also think about screening to prevent some of the consequences of certain illnesses. But the real challenge with this is that if we continue along our current route, personalization is practically impossible. And what I mean by that is we can build lots of risk models. That's fine. But how are we actually going to implement any of them? And to give you an example, if you were to talk about population level screening, which is clearly my interest, if you want a risk-based screening program, you need to have something that can actually target the whole population. So you need to have the ability to ask these questions of everyone, or you have to use something like an electronic health record and hope that the data are good enough, which in almost all cases they're not. And given this, you're going to end up asking physicians or allied healthcare professionals to fill in more and more and more information about every individual at every occasion that they come there. And I really want this to be something that is front and center of your future efforts in this kind of area, is thinking, how do we build a system that actually integrates so that these models are not all disparate, they're not all layered on each other. There's some joined up systems thinking, because it's the only way that we can actually do this at scale. So in terms of the main aspects of this talk, I want to talk predominantly about automated machine learning, and then using that as an example into risk prediction, some of the perils, pitfalls, how it should go about, and then some examples at the end. So we'll start with what is automated machine learning, and then why we should use it in the context of risk prediction, followed by when we should use it, and lastly, how. So thinking about what? Many of you will have an idea of automated machine learning. But if we think about the steps that we would take to build a clinical risk prediction model, we're looking at developing it, evaluating, deployment, and then long-term monitoring, and all of the little bits of this in between. Now, if you were to use an analogy from the stages of automation in car development, there are essentially 5 different stages. The first being no assistance. I'm not sure that anyone would really use this anymore, but what I mean by this would be you manually encoding, say, a logistic regression model. It's feasible, but nobody would do this. Developer assistance. So developer specifies aspects of model development and is assisted by software. It's largely where we are at the moment. So you know roughly what you want to do. You want to use a logistic regression model, and you just tune the software to do it a little bit. Partial automation, that's kind of where we're moving. So that might be something like looking at different ways of optimizing the hyperparameters that are going to a model. You're not doing this manually, it's being done under the hood. A very high level automation is when you're making the key decisions but software is performing almost all of the steps automatically. And then in theory, there's full automation where your software could go off and automatically develop, train, evaluate, and put into practice a model for a specific risk prediction problem. Now, where are we? As I mentioned, most people will use packages that exist to do risk prediction. So that's a form of automation. Um, that could be scikit-learn or scikit-survival if you're in Python. Can be different languages will have their own different packages. But when I mean partial automation, I came back to that example of optimizing hyperparameters, but you've also got hyperimpute, which is built by the lab, which is all about different mechanisms to automate what the best approach is to imputation. And then higher levels of automation, well, here I would put something like the autoprognosis package, but there are other versions of this, essentially where you have a clinical problem and then the steps are taken between that, all the way from pre-processing data through imputation and then development, and that is all done automatically. And then full automation, well, we can have a debate about this, but I'm not sure, well, we're certainly not there yet, whether we'll ever truly get there within a clinical space. Maybe not in my lifetime. We'll get close, I expect, but not actually there. So overall, the argument that I'm trying to make about automated machine learning is that it can be considered on a continuum and that we're already using it. It's just a form of abstraction, and that in abstracting, you can augment both experts who really should know what they're doing and non-experts who may come with more of a clinical bent and actually want to do something in the real world. A key thing with automated machine learning is that it can improve the quality of risk prediction tools. And I'll come back into that in a second. It democratizes access to state-of-the-art models, and fundamentally, it's the future. Every time that we improve, we'll just think of this as ML rather than the AutoML that it actually is. Why? I've touched on some of these arguments, but why would we want to use something like this rather than doing it manually, which we might feel we have more control over? Well, fundamentally, there's no free lunch. A clinical risk prediction model issues a probability that an individual will have an outcome within a certain time frame, or it provides some sort of scoring threshold that determines further action. But after you start this process, you have to deal with your variables, manage the missing data, iteratively fit different models to the data. And then you could use all these types of techniques. What are you going to choose? You could even add survival analysis, which might be the first approach that you take for most clinical tools. But when you think about all of these different approaches, you get nearly, well, over 1,000 different possible combinations. And as a result of this, what happens is we just tend to use the ones that we are most familiar with. Survival analysis, for the sake of argument. And in most cases, that might work quite well for most problems. But it's a little bit like turning around to somebody and saying, I'm sorry, there's lots of different chemotherapies. I'm not entirely sure how to prescribe them, so I'm just going to give you the one that I've used for the last 10 years. Coupled with the sheer volume of different approaches you can now take with machine learning, there's the software engineering behind this. Are you going to use Python, Julia, R? Which different framework within that are you going to then use, which package? And even when you get there, coding something up in order to be able to optimize your hyperparameters for, say, an XGBoost model, which is what this snippet might do, is non-trivial for most people unless they have got a background in programming, and most clinicians don't. This is then rendered even more complicated by the fact that you have 1,015 different combinations if you just do it once. But then what about ensembling? There you have multiple different approaches that you package together. So overall, there's no single algorithm for all risk prediction tasks. There really is no free lunch. At the moment, we treat it a little bit like there's a wonderful quote that's, we're kind of happy that we found our model as if it were just behind a gooseberry bush, waiting for us. And that was it. We don't really understand why we got there, all the different choices that were made. We hide that away. I don't think that that's really good enough. It's very complex to program multiple approaches. But as I came back to before, you're not going to prescribe a different medication simply because you didn't know the dose. So you would look this up. even if you look it up, doing it is really hard. Don't repeat yourself. You could theoretically choose to create your own version of an ensembling algorithm. But unless you're very, very good at this, you're going to encode errors. And I think the focus within clinical risk prediction models should be on solving real clinical problems. A lot of effort in data science and machine learning goes into programming, building these models. That's where a lot of our time is spent. And there's quite good reasons for it. It's it's quite fun, actually, if you're doing it. And in many respects, it's quite easy. You can go away and do it yourself. The task of actually getting it to solve a real clinical problem is much, much harder. And I think that we should try and refocus a lot more of our effort onto that rather than wrangling software. But probably most important is that we should get it right the first time for a given problem with given data. What I mean by this is that often we repeat clinical risk prediction algorithms. So I think, I can't remember the exact numbers, but off last count from one of the systematic reviews, there's something like 200 cardiovascular risk assessments, and that's for primary prevention alone. That's not really necessary, and it suggests that what's happening is we're not getting it right the first time. And often this is the case. So in one of my areas of expertise is in lung cancer screening. And here there was one of the initial models published using logistic regression back in early 2010s. And the model does quite well. Not possibly the best model of all, but it does quite well. And 3 or 4 years later, in a very, very highly esteemed clinical journal, a Cox model that uses almost exactly the same variables was published, showing that it was better. So it was using the same, sorry, not just the same variables, the same original data sets. That's 4 years, or in this case, it was 4 years between the two papers, 4 years of wasted effort because we were using the wrong model when we then decided to do some more prospective evaluations. We should have been trying all of this stuff all at the same time from the beginning. So Mahela and I actually ended up writing more about this, and you can go and look at that if you're interested. But our key thing, though, if you do want to go and use things like automated machine learning, is that they really should be open source. And I think that this is important because if you don't understand what it's doing and you can't tweak it, that is a real problem. You do suddenly give a lot of control to something that you don't necessarily understand that well. And there needs to be a community that does understand what's happening underneath it. A little bit like you can be the driver of Formula One car and you might not know all of the engineering behind it, but there should be some engineers who do. Now, when might you use this? Well, with a suitable data set, I think it can be argued that automated machine learning should be perhaps the first approach. And the reason is that you will then very quickly know whether or not, especially a package like autoprognosis, which will essentially be able to iterate through lots of different models, lots of different pipelines, build these out for you, and work out whether there are actual advantages to using machine learning in your problem. There may not be. It can also give you a head start in working out what algorithmic approaches appear to provide the best results. So even if you decide you didn't want to go and actually use the automated machine learning software to build the production-ready model, this gives you a way of iteratively trying lots of different approaches in a robust manner before then selecting how you want to take it forwards. I think, though, as a caveat, you really do need to consider your data set because if it's very, very small, it may well be that you can't actually answer the question you're posing, or machine learning may not be very appropriate in this case. It has a tendency to overfit in very, very small data sets. You might find that a more straightforward linear regression model will actually do the trick, roughly. So how? Well, again, I'm going to use automated machine learning in the context of risk prediction. But the first thing, perhaps seemingly boring, is the planning bit, because you want to be like Roadrunner, going straight through rather than bashing your head against the wall. So what is the problem and what already exists in that space? And when I say what already exists, what models exist, what solutions have been tried? Is it that We don't use a risk prediction model in that particular context because the added value is probably going to be relatively limited. And I can come back to some of that in later on. Who is going to use my risk prediction model? Is it designed for members of the public? Are we going to send them text messages asking for this kind of information or guide them to a website? Is it going to be for healthcare professionals? This matters later on for how you choose to implement it, but it also should give you pause to thought when you're thinking about questions. If you're going to ask questions that are particularly detailed, like, I don't know, have you been exposed to asbestos? And you send that out to the real world, you're probably going to find most people, A, don't know what asbestos are, B, have absolutely no idea if they've been exposed. So the value of your variable, even if it looks really nice, probably not great. When will they use the model? Are you expecting somebody to use this on their own with the clinician in front of them? Again, this is all about thinking through the trade-offs. If you're going to use the model and you expect it to be done with a clinician in front of you because it has a few complex factors. So, for example, one of the most famous cardiovascular disease risk prediction models for primary prevention in the UK, one of the questions is, what is the standard deviation of the last two blood pressure readings you have? Now, that's not even automated. If you're expecting a clinician to do this, you might need to provide some tools that facilitate the entire process. And you do have to think about how complex it is and whether they will actually use it in practice. Why will they use the model? It kind of comes back to my first point, but how much added value are you giving them? And do they really understand this? And where are they going to use it? Again, it's quite related to the when question, but a model that you have to use in a GP surgery where you're competing for that GP's 8 minutes with a patient is something you have to bear in mind. And actually, when I say how, this also relates to electronic health records. These are often put up as a panacea that you can just, if you built it in an electronic health record, then you can deploy it in an electronic health record. But as you'll find in several lectures time when you're talking about data-centric problems with Nabil, but electronic health records are incredibly flawed, and they may well be very valuable if you're, say, building a risk prediction model for a treatment, and you can guarantee that the individual in front of you, the clinician, will have all the information that you possibly need. But if you're thinking about it at a population scale, the chances are the missing data are going to be dramatic, and the probability is that the missingness will correlate with some of the features you probably are interested in. So, for example, in lung cancer, we know that electronic health records are more likely to miss smoking details in people from lower socioeconomic groups, but people from lower socioeconomic groups are more likely to be smokers and therefore more likely to be eligible for lung cancer. Squaring that circle is challenging. Then, so I've thrown a whole bunch of problems at you, and now I want to create one more, which is contextualize your problem and think about the person rather than the disease. So, coming back to what I said beforehand, if you're just in the UK going to use guideline recommendations to determine whether somebody should have lung cancer screening or cardiovascular disease risk reduction, so statins effectively, that at the moment requires 35 different data points to be added across separate specialist websites just for those two risk scores. And if you tot up the amount of time and assume that people work nearly without breaks except for lunch, you'd need somewhere up to 100 people working a whole time for a whole year, all day, every day, just phoning people up to risk score 1 million people, assuming it takes 5 to 10 minutes per person. That's an awful lot of time. So, for example, in the UK, there are 28 million people who are supposed to be risk assessed regularly in primary care. We know that this simply doesn't happen. And as a result, there are several 100,000 cardiovascular events, things like heart attacks, strokes, that happen every year that could have been prevented. And part of the reason is the complexity of how we are doing personalization. Performance. So, how are we going to build our clinical risk prediction model? The first step is our data. So What are the development data sets? What are the external validation data sets? Do we have all the ethics, the sources? Are we going to wrangle that? How are we going to manage it? Missing data and imputation. Having walked into the discussion at the end, that's obviously something that's been covered, but the other thing to bear in mind is not just missing data and imputation when you're building it, it's missing data and imputation when you are putting it into practice. What are your candidate predictors? How have you selected these? How realistic are they? How meaningful are they? And then we come to the actual model development and feature selection bits, followed by how well is it going to do? So those would be your five predominant steps. Note though, we haven't yet got our model into practice. So we've built our model, we've written a nice paper, and we're feeling very good about ourselves. It's still not in clinical practice. So we'll come back to that later. Data. This is an under-considered area. If you want to build a risk prediction model for your local hospital about probability of being admitted with something, and you've only got 200 patients in total and only 10 of them had an event, the chances of you being able to answer that question very reliably are pretty poor. So do think about the data that you have. When you train your models, you really have to think about how you're going to split your data sets up, training and testing, bootstrapping. There's lots and lots of manuals on exactly which types to use. Split sample is the most common in machine learning, but actually bootstrap optimism is probably the most statistically robust. Missing data and imputation. Again, what are the implications of this in practice? And I think, again, representativeness. If you're going to get somebody to use your model, you're going to have to persuade them that it's not going to unfairly bias different groups. This can be really tough because most data are not that good, particularly in different minority groups. There are ways to get around that. Some of this might be supported with synthetic data, again, something you're going to have a talk on. But fundamentally, this is something you'll need to bear in mind. And it doesn't mean that you can't do the problem. It just might be that this is a large caveat, and when it's put into practice, it's going to need a lot of monitoring. The value of information is one of my favorite things. So what we mean by this is how many predictors do you actually need to solve your problem? Now, remember, when you're doing clinical risk prediction, you're not trying to work out necessarily a causal relationship. It's helpful if there's a causal relationship, but that's not always what you're most interested in. So what you care about is building the most predictive model that you possibly can, given various real-world constraints that I've put from before. And this is an example from one of Fergus's papers on autoprognosis, where they show that after a certain point of adding the variables, they weren't getting any benefit in what's called the C-index, which is a measure of discrimination. Essentially, how good is it at telling you whether the person has got the outcome or not? Now, you can take this even further. Because if you can see here, the comparator model had about 20 different variables. It's quite a lot of variables. And again, as I said beforehand, think very much about, is this for a situation where I know I can guarantee I can collect all the variables, or is it something where actually I'm making my life really hard and the life of everyone who's going to use it? The value of modeling. Again, clearly everyone here is interested in AI and medicine in some way, shape, or form. The great thing of that, of course, is that, as I mentioned beforehand, there's lots of different machine learning approaches you can take to solve a different problem. However, one of the reasons why the tried and tested Cox models or logistic regressions are still so prevalent is because they often work relatively well. And so, as well as thinking about an initial kind of run with, say, autoprognosis or another auto machine learning piece of software to really see what benefits machine learning is going to give you, you should simultaneously put together, it can be completely linear, you can put in a few interaction terms, but a Cox model or a logistic regression model, just to make sure that there is enough added value. Validation. So these are the core things that one should be looking at. The discrimination of the model, in other words, how good is it? The calibration, this is really very important. Most models, I mean, and when I say very important, most models will be miscalibrated in different groups. If you're moving from one geographical context to another, the chances are there will be some miscalibration. You can recalibrate a model, so that doesn't invalidate it in any way, shape, or form. But you really need to be aware of this because, again, once a model goes into routine clinical practice, the chances are it will be used amongst groups for whom the calibration is much poorer than you would otherwise have hoped. And the implications of this are important for when you actually consider how you build a model. So, for example, let's say you have built this amazing model that has a discrimination of, I don't know, 0.9, really very good. You're terribly happy. And then what you find with the calibration is that in some underserved communities, it massively underpredicts. Say that the calibration curve would mean that it's 50% underpredicting. So it's saying that rather than somebody having a 10% probability of dying of this condition in the next 5 years, it's predicting a 5% probability. Now, that's a really big deal for those individuals. It doesn't matter that that model was perfect and you put in 5 extra variables that require 3 different types of biomarker taken over 2 months. That is irrelevant because the calibration is so poor in that particular group. So trading off these two things are important. And it just then comes back to when you're thinking about the complexity and all these different trade-offs, there's no point building the world's best model if it doesn't actually work very well in terms of the calibration. And it might mean you need different models in different groups. Again, this isn't a problem. It's just something to be aware of. The overall performance can be measured with things like BRIA scores. These are called proper scoring rules. And then finally, you've got clinical utility. So in the short run, this can be done with something called decision curve analysis or net benefit. I can show you an example of that later on. But more detailed versions, decision analytic models, are usually required before you can put something into practice. And what these models are showing is what benefit there is from using this kind of model, your kind of risk prediction model over the lifespan of said patient. Now, this is what I mean by an example of trying to look at different models across different deprivation indices. So IMD in the UK is called Index of Multiple Deprivation. It's a statistical measure produced by the government, and we do it at very low geographical areas, so relatively homogeneous geographical areas. What you can see is that some of the models, this is lung cancer, but some of the models, for example, the PLCO, works actually unusually worse in those who are least deprived than in those who are most deprived. But bearing that in mind is important. Once you've built your model, you need to be able to understand it. So on the left-hand side, I've given you hazard ratios. So this comes from a Cox model. These are readily interpretable in some respects, although in general, having to interpret the binary versus log term or squared version is not actually something that is totally straightforward. In machine learning, there are lots of different approaches. One of the most common is called SHAP values, and this is a good way of being able to show how or explain how the variables are operating in your model. Coming back to the lab, Mahela's team have built something called Autoprognosis 2.0, which solves some of these problems for you. So it's an open source, clinically focused automation machine learning package. It optimizes full pipelines, but you can actually turn off that full pipeline. So if you only need it to iterate through the different types of machine learning algorithm, you could do that. And its real advantage is one overarching framework. So you don't have to go and play with learning all of the different constituent algorithms on their own. There is one way that will allow you to simply approach a problem from Cox regression the whole way to a neural network. That can be very valuable. Kind of coming back to an overarching common pitfalls. First is too many variables. Lots of papers will have models with 50 or 60 variables in it. I don't know how they think that those are going to be used. The very few situations, perhaps outside of ITU, may be the only place where those kind of things could be used. But you'd need somebody to be in serious monitoring for that kind of variable to make sense. Unrealistic variables comes back to my example of asbestos, but also imagine asking the whole population about their family history of a particular cancer. A lot of people will not totally understand what you mean. So even how you ask that question will matter. But often people don't really know. Beyond their parents' generation, information can become quite sketchy. Model explanation is vital. You won't get used if we can't explain your model. Subgroups, again, vital. Too many models are published with overarching statistics. It was good in aggregate, but how good was it in X or Y age range? How good was it in men versus women? These things are really important. And finally, your model needs to be validated. In some cases, that can be impossible to do immediately. It doesn't mean that it won't need to be done at some point. So now you've built your model. Sadly, it hasn't stopped here. You've got to think about how to deploy it. The UKCA or CE marks. So the UKCA is the new version for the UK, but it's essentially a CE mark, which we have in Europe, as you need to be classed as a software device. Who's going to maintain this model? If you build it in academia and your grant funding runs out, who's going to keep it going over time? And then you have to think about how you really show the benefits of using this approach. If no one's ever used a risk prediction model in your clinical problem before, why is it valuable versus using 3 or 4 different relatively straightforward clinical criteria? So, for example, why should you use a lung cancer risk prediction model rather than just saying, I will screen people who are aged between X and Y who've smoked at least this many cigarettes per day for at least this many years? It's much easier to use that latter version. How are you going to monitor it in the future for model degradation? Models change over time. It's because the population changes. Again, coming back to lung cancer, in the 1950s and 60s, a large majority of people may have smoked. Nowadays in the UK, it's 12%. 2 decades ago, it was 20%. The 20%ers are going to take up the large majority of our lung cancer patients, or going to be the large majority of our lung cancer patients for the foreseeable future. But at some point, these models that are built in older cohorts will probably be over predicting for the average person. I'm aware that I have cantered through some of this, so I'm just going to give one example from personal experience to try and bring it all together before leaving lots of time for questions. So this kind of comes back to some of the work I did in my PhD, but it was all about risk-based lung cancer screening. And most countries don't do this. We don't have lung cancer screening programs in most locations, but they're being built. So they have been recommended in the US and they're being built all over Europe. And why are we doing this? Well, I think this graph kind of sums it up. We have doubled lung cancer survival, but gosh, is it bad? So this is net 5-year age standardized survival. And the reason behind that is that, at least in the UK, nearly half of the cancers are diagnosed at the latest stages. And 70% is stage 3 or 4, so incurable stages. We know and have known for some time that if you were to screen, you can reduce deaths by about 20%. So this is the rationale for why we're going to build this program. And in the US, they have decided to take a relatively straightforward approach. You can get screening if you're aged between, say, 50 and 80. You are either a current smoker or if you're a former smoker, you stopped in the last 15 years and you have smoked what we would call something like 20 to 30 pack years, which is just a measure of how long you smoked and how many cigarettes you smoke on average. It's quite simple in a clinic to ask 3 or 4 questions, tot up those things and say to somebody, okay, you're eligible. Despite that, lung cancer screening in the US, the uptake is actually less than 10%. So risk-based programs are hard to do. But in the UK, we've gone down the full risk-based approach. And so what we do is we would trawl GP records for people who might be eligible based on their age and their smoking status. A good idea, quite pragmatic, but flawed from a public health perspective because smoking status is often inaccurate. The inaccuracies, as I said beforehand, correlate with deprivation. They also correlate with ethnicity. And if you're in a place like London, one of the most diverse places on earth, that matters. You send individuals letters asking them to call a screening centre where then they, if they do call, somebody has to sit and talk them through their individual risk. We use two different risk prediction models together as we weren't entirely sure which one to use. And that's 17 variables, takes somewhere between 5 and 10 minutes. Often it's quite quick. In some cases, it can be 20 plus minutes, depends on the individual. Depending on their risk level, you invite those who meet a particular risk threshold for screening. Building your risk threshold and deciding what that risk threshold is a whole area that could be a lecture in itself. Now, to do this just for lung cancer, we would have to have about 600 people sitting in call centers working all day, every day, just to do this risk scoring. So as I mentioned beforehand, that's a lot of people when you start thinking about the fact that we're also supposed to be doing it for cardiovascular disease and other conditions. Indeed, if you look at the people who are eligible for lung cancer screening, more of those people will die of heart disease than they will of lung cancer screening. So that comes back to my point earlier of integration. Now, what we showed using autoprognosis, or a much earlier version, is that if you ensemble, so you use the power of putting together lots of different models, you could radically reduce the number of predictors. So we got it down to age, smoking duration, and pack years, and I think we could probably go further in the future. And so what we did was invert the usual paradigm where you add lots and lots of predictors to one model to hope it improves the quality. We took it as granted that all models are wrong, but the chances are they're wrong in different ways. So that's the basis of ensembling, which means that if you put together lots of different models over time, mathematically, as long as the models are not correlated or the errors aren't correlated, you will end up with a single model that is better. And no one, when they're actually using the model, needs to know that underneath are four different models actually doing exactly the same thing. All four models take the predictors, run them through the model, and spit out a probability, which is then averaged. Now, based on the weights. We managed to show that in multiple different data sets, and actually recently been independently validated, that these UCL models were as good as these other more complex models requiring 3 or 4 times the number of variables. But most important, this is where the decision curve analysis is that I mentioned beforehand, it makes no difference to the number of cancers you pick up using our simple models. So what these curves are showing you, and the fact that the what you want is these two curves. These curves are overlapping more or less, especially when you put the confidence intervals. And the same here, is that at any given risk threshold that you choose, a risk threshold is a choice. The number of cancers, so the net benefit over screening everyone or using the current criteria, is greater. So you're picking out more true positives for every false positive, or for a fixed number of false positives. In other words, you're basically just picking out more of the cancers using these models. And that was something we did last year. I hope that that was understandable. It was quite a rapid talk through. Should we start with questions if anybody has them? There's quite a lot going on in the chat.
Yep. Thanks, Tom, for the excellent talk, and I'll be moderating the questions. So the first question comes from Nicole. I don't think Nicole can speak up, so I'll just pose a question here. So Nicole's question is, maybe I understood, but you're hoping AutoML will be useful to provide ML access to clinicians more easily. How hopeful are you that can happen, considering the background knowledge required for missing data imputation, feature selection, and feature engineering? or even being able to frame the problem correctly? Are there ways to automate some of the human heuristics behind some of the early decisions?
Yeah, that's a really good question. So I'm in two minds, and I'm going to answer it in slightly different ways. The automated machine learning, particularly when coupled with LLMs that have guardrails in front of them, can help with a lot of these problems because they can provide some way of allowing you to interact with these machines more naturally. It's not perfect, but it is a way that might work. And as we get better at putting guardrails around LLMs, and this may actually even be shown later on in the course, something that the lab has been working on is how do you use, say, a chat GPT like infrastructure to be able to talk through these kind of problems with an LLM and build the model alongside. So you kind of couple the best of both worlds. You don't need to rely on ChatGPT going and building a model, doing something that you're not entirely sure what it's actually doing. You can control the code behind it, but you can also allow it to support you with missing data, imputation, feature selection, and feature engineering. Um, Now, there's a kind of second question, which is, at least in the short run, how desirable is it to give people, so how desirable is it to massively increase the number of risk prediction models if they're not going to be of high quality? I think that it's a slightly different question. I think that you do need some experience in order to build something that is going to be useful. But having said that, I think that these tools can allow people, particularly those who've gone and say they're clinicians and they might have a master's level understanding, be it through a master's in public health, a master's in epidemiology, something related. So they kind of have a relatively good idea as to how to think through the problem. Then this will help you with most of the coding problems. Because a lot of the people that I come across, they might have a vague idea how to do it. They just have absolutely no idea how to program it. And I think we're getting closer and closer and closer to being able to make that a reality.
Okay. So I think Nicole has other questions, but I will sort of let other people go first, and then if we have time. So the next person is Jake. Jake, do you want to ask your question?
Yeah, of course. So it's kind of an addendum to what you were just talking about, actually, Tom. But thanks for a great session. That was really, really interesting. I was wondering, there's a lot of talk in the field, I suppose, of, where do we really draw the line between fully automating something and, letting that sort of go off and not having as much human interpretation or human intervention. Like, where do you see the line drawn in this sort of way, I suppose?
Um, so I think that most of these, so I'm going to take a pure, actually, I'll look at it from two perspectives. One is risk prediction through, say, radiology, and another is just risk prediction through variables that you might have in a data set. Um, the In terms of full automation, you're unlikely to get to a situation where you're going to fully automate a lot of the clinical decision making because I mean, you could probably program some of it up. So if their threshold is over X, then they get Y, and link guidelines in. Um, the Actually, taking it one step back, from my perspective, as long as something has been independently validated and evaluated in generalizable cohorts, then I am not personally that bothered by the automation element. But I don't think that we're there. So when I mean that, let's say you were to put in a new model for a particular hospital. From my perspective, it doesn't matter if a large part of that is automated, so long as the processes are in place for ongoing monitoring, so that you're collecting the right data to be able to change, to see what the implications are of your model. And this is having a human oversight relatively frequently. Um, so I think you can do some of this within guardrails. In terms of automation from, say, a clinician's perspective, um, I'll be blunt, I don't think most clinicians have any idea how the tools that they're using are being developed. In some respects, it might as well be magic. And I don't really see the distinction between, say, a fully automated model that might have some flaws and some of the ways that we do clinical medicine at the moment. So a lot of the technically risk algorithms are extremely simple. They might be, we use things like Chad's-Vask and stroke and things, which are literally you tot up a few points based on a few different criteria. Most people think that these are the gold standard because they learned about them in med school. How they were developed, the fact that they were developed an awful long time ago, and nobody quite knows how good they are anymore. That to me is a real problem. There's no real distinction between that and full automation. If you're willing to use something as poorly conceived as that, why can't you use full automation?
Mm.
But the caveat there being, I really think these things have to be stringently evaluated before they go into clinical practice, and there needs to be more real world assessment. So if you can build the infrastructure for the real world assessment side of this, when I say real world assessment, I don't mean pure observational data. I mean, say, again, I'm going to give the screening context, but say you're going to implement a new risk algorithm across the UK. You can randomize different hospitals to be using that risk algorithm versus another risk algorithm in a different hospital, and use that as a form of cluster randomization to really show how is this going to work when it goes into the real world. Once you've done that kind of real world evaluation and you have plans in place for monitoring, then frankly, it doesn't matter to me. I think that there's a lot of value in automation if it improves. I'm quite utilitarian, so if it improves the net benefits of some of the guideline pathways we're doing, I think is probably a good idea. Humans make errors all the time. We don't allow machines to make any errors at all. I think that that's probably a balance that we need to think about. But yeah, I feel a little bit like I've given a very woolly answer to that because I think that there's so much that goes into it, be it the ethics of this, the challenges in different circumstances, but roughly
That's
speaking.
exactly what I was hoping for. So thank you for giving your perspective. I just wanted to get like an overview, really. So thank you.
No problem.
Okay, so the next question is from Samuel. Samuel, do you want to speak up?
Hi, thanks for the excellent talk, Tom. I was just wondering if there was any examples of a prediction model developed using an automated pipeline that has actually been deployed clinically and is in use.
To my knowledge, no, is the simple answer. We are going to push for the lung cancer model to go into practice, and that was built using admittedly a very early version of autoprognosis, but it was built using automated machine learning. In reality, there shouldn't be any reason why you can't use an automated machine learning software so long as your evaluation is as rigorous as you need it to be. Fundamentally, it's no different from somebody who's used a package like scikit-learn or something. It's just a little bit more sophisticated than that. You still need to have all the evaluation on the other side. And if your model stacks up, particularly in independent validation, then there's no reason why you can't use this. Having said that, getting your model to CE marking, getting through the software regulation bit, there you run into more complexity. But in principle, no, there's no reason.
Thanks.
Okay, thank you. The next question is from Rabindra, if you want to speak up. I can also read the question. It's quite short. So the question from Rabindra says, how to determine that enough value has been added while using complex models instead of simpler models?
Very good question. I don't think you have a particular answer to that. Sorry, I don't have a particularly strong answer to that. I think you need to consider the three major elements. So how well is your model discriminating? So what's your C index for the sake of argument if it's time to event analysis or AUC otherwise? And what does your calibration look like in the different subgroups? So it may well be that a complex model doesn't add very much to your overall discrimination, but it does improve it in, say, some different groups. So you could even ensemble a model where you have built a specific model for women and you built a specific model for men because an overarching model didn't perform as well as it should have done. Those could be two simple models combined, but you may not overall improve the total performance, but you might just improve the performance in one small subgroup. That would be enough. What I was really trying to get at is often you'll see that somebody saying that claiming that their model is better because the discrimination has gone from 0.806 to 0.809. It's probably not worth it in the grand scheme of things if you are then having to do loads of layers of machine learning to get it versus the 0.806, which was, say, a Cox model. The reason I say that is because not because in theory you can't get something better out of that, but more because there's a lot of effort in changing, say, risk models or using something different. They'll only do it if it's actually valuable. If you're not proving that it's really adding much, you're not going to be able to persuade people to change their practice.
All right, thanks a lot for the answer. Our next question is from Christian. If you want to ask your question. I can.
Small data sets. So when
Yeah,
I was
yeah,
not a good idea for a small data set, what does small stand for? I think that kind of comes back to again, difficult to know exactly. Slightly depends on the context. But machine learning does have a tendency to overfit things. If you're going to then trial multiple different algorithms and you've only got, say, 20 people who've had an outcome and only, I don't know, 200 people overall, the likelihood that you're going to be able to generalize that algorithm to a different situation is probably relatively small. And under that circumstance, you might be better off just fitting in quite a simple, say, linear, or again, you can add in the odd interaction. But you need to think about how many predictors, so the complexity of your model against the number of outcomes you have. There are rules of thumb in that, and you can kind of extrapolate those rules of thumb to automated machine learning. What I'm saying is more heuristic here. It's not that I've gone and done lots of simulation studies of different small data sets, but in general, you probably don't need automated machine learning. You may not even need machine learning if your data set's tiny in a clinical context. You just might end up overfitting it.
Okay, so the next question is from Ivan. Ivan asks, are there any steps being taken to improve the quality of the data?
Yeah, there are, but it's not going to happen anytime soon. And that's mainly because if you're going to improve the quality of the data, you've got lots of different contexts in which you're doing it. And the trouble is most things are not coded in exactly the same way. A lot of improving your data means getting more of it. If you're asking your healthcare physicians to go and collect more data, they may or may not comply. It depends on whether they see the value in all of this stuff. So if it's about ensuring that everything is coded in the same way, well, we'll probably get a little bit better at that over time. There are standards. FHIR is one of them for improving the coding of your data sets. Having said all of that, even in some of the best places using the most state-of-the-art electronic health records, when we tried to build some synthetic data off it, we essentially found that the coding of the different conditions was so shocking we couldn't actually even find the patients from some of the records, and that was a real problem. So yes, but it's not going to happen anytime soon. So you should bear it in mind when you build a model.
Okay, so it's approaching the end of the session, and we have like tens of questions that we have not gotten to. So I would sort of be curious what both Tom or Andreas thinks. How do you think we should sort of process the remaining questions? If you have any suggestions.
I mean, I don't know how time constrained you are, Tom, but you might answer a few in the chat if you have like.
Yeah, I'm just going through. So I'll go and answer them in the chat as well. But the just thinking about it, there's two or more questions on explainability that we can try and put together. So what if I so I'll just put in the 2 minutes, I'll try and answer some questions on explainability, working backwards. So Yuan Shang has one on 3 variables versus 10. And wondering about overfitting. Yeah, it was something we were concerned about. So it's been validated actually in because I would like this model we really wanted to see whether we could use automated machine learning to get something that could be production ready. The model has been validated in 10 different data sets into 300,000 people. So yes, it works. But it was a concern. And there's nothing you can do except validate it in extra data sets to check. I'll come back to Simon's comment on federated learning because that's really interesting. And factoring in explainability into the model selection. It's true that logistic regression is inherently more interpretable, but I suppose that does slightly depend. So yes, a straightforward linear model that doesn't have interaction factors, etc., is quite interpretable. But the minute that you're adding in lots of different polynomials, most people don't think in that kind of mathematical approach. So the interpretability then becomes a bit more challenging. Sure, whether your odds ratio or whatever, that is an easy way of doing it. The ensemble bit, you're not necessarily explaining every single model underneath it. You're explaining what the aggregate model is doing. And these things like SHAP produce models of models. So there are limitations to that approach, but they're not bad. And arguably, some of the output from some of the more machine learning approaches to explainability are more intuitive, quite simply showing you which variable was doing more at what point, or metrics of how these variables change depending on the value of the variable, the importance of the variable depending on the value of the variable. So in terms of where do we draw the line, I think explainability is an important and necessary step, but fundamentally you need something that works well. So as long, again, as it has been validated in lots and lots of different settings, and then ideally in a real world context, I think that should be sufficient. I will try. I'm appreciate we've got to 12, so I'll answer as many as I can in the chat and get everyone's hair.
That would be great. All right, Andreas, do you want to take over?
Yeah, sure. It will only be for a second. Thank you very much, Tom, and also Guao for the moderation. It was a very exciting talk and lovely to see all the engagement in the chat already. So thank you very much for answering those. I will hand over straight to Nabil, who will get us into the session by Dr. Julia Ive. So looking forward to that. So Nabil, over to you.
Yep. So hi, everyone, and welcome, Julia. So it's my pleasure to introduce Dr. Julia Ive. She's an associate professor in healthcare AI at University College London. I think we're really privileged to have her to speak on large language models. Her research really focuses on data-centric and human-centered approaches to large language models to promote responsible innovation in healthcare. And she's had many recent projects, some of which have been to detect and mitigate bias, protect privacy in pediatric mental health care using synthetic text. She's been previously at Queen Mary University of London and Imperial College London. So Julia has really been at many top institutions. And I think especially being the person to introduce large language models at the summer school, she's a real expert in language modeling and multimodal machine learning. And she's been involved in teaching and organizing AI and NLP courses for master's students and industry professionals. at the Alan Turing Institute. So I think there's probably no one better to be kicking off the summer school on the large language model side than Julia. So over to you, Julia, and thanks so much.
Thank you.